Remember we said that for a confined aquifer, the heads generally don't change much with depth. In other words, if we measure, say, a head of 15 feet above datum at one point in a confined aquifer, we'll measure about 15 feet at any other depth in the aquifer at the same point. This means that if we insert a set of piezometers at various depths into a confined aquifer at a given point, water will rise to about the same level in all of them. Although the heads don't change much with depth, they do in general change with horizontal position. For example, if we perform the same experiment some distance away, we might find that the heads are everywhere 16 feet, and at another point we might find that they're 18 feet above datum. The key point is that at each location on the surface we can associate a unique value of head to the confined aquifer. If we connect these head elevations with a surface, we define the piezometric surface of the confined aquifer. That's this red line here. The slope of the piezometric surface tells us which way groundwater is moving in the aquifer. For example, in this diagram, the piezometric surface slopes to the left, which means that the groundwater is flowing horizontally from right to left. The Dupuit assumption basically says that the same idea applies to unconfined aquifers as well. Remember that the head at the water table is the elevation of the water table. According to the Dupuit assumption, the head beneath the water table is approximately also equal to the elevation of the water table. So if the elevation of the water table is 20 feet, then the head in the unconfined aquifer will be 20 feet below the water table as well. If we were to install a bunch of piezometers at various depths, they would all see water rise to about the same level, the level of the water table. At another location, the water table might be 19 feet above datum, and this would mean that the head is 19 feet at all depths. Same would go if the water table were 18 feet above datum. The Dupuit assumption allows us to infer the direction of groundwater flow in an unconfined aquifer from the slope of the water table. For example, in this case, the water table is sloping from left to right, so in the left-hand side of the diagram, so this means that groundwater must be flowing from left to right. This flow is approximately horizontal. The only place the Dupuit assumption seriously breaks down is near places where we know the groundwater has a significant vertical component flowing either up or down. For example, near obvious recharge or discharge areas. But as long as we're at least 1.5 thicknesses away from these areas, the Dupuit assumption holds pretty well. In this case, I've defined the thickness of the aquifer as B, and as long as we're at least 1.5 B's away from this obvious discharge area where a stream appears, then the Dupuit assumption can be used not only to get the direction of groundwater flow, but actually the velocity of groundwater flow. Even when we're closer to this obvious discharge area than 1.5 thicknesses, we can still use the Dupuit assumption to get the direction of groundwater flow, even though it can't be used to accurately determine the velocity. Here's an example from South Florida where the elevation of the water table is contoured. It's probably a little hard to read these, so I'm going to enlarge a portion of the western side in the next slide. Here I've enlarged a portion of the western side, and you can see that the water table ranges from about 9 to 3 feet above sea level and slopes to the south. We can use the same technique we used with the confined aquifer to infer the direction of groundwater flow in the unconfined aquifer by drawing a smooth path that goes from high head to low head and crosses each contour at a right angle, like I've shown here with the red arrow. Here's one more application of the Dupuit assumption. We have an unconfined aquifer sitting above a confined aquifer, and it's separated from it by a confining unit. Let's assume that this confining unit is leaky. That is to say, it has a low but finite permeability that allows some water to slowly pass across it. The question is, which way will this water move? Will it move up across the confining unit or down? Let's assume a datum located at the bottom of the figure shown by this red line. Now remember, groundwater always flows from high head to low head, so to determine which way water will flow across the confining unit, we need to know the relative heads above and below, at the orange dot above and at the purple dot below. The orange dot is located in the unconfined aquifer, so the Dupuit assumption says that the head will be equal to the elevation of the water table here. That's this orange line. The purple dot is located in the confined aquifer, so if we assume that the head here can be described by the piezometric surface of the confined aquifer, then the head at the purple dot will be shown by the purple line. Since the orange line is higher than the purple line, the head in the unconfined aquifer is higher than the head in the confined aquifer. This will thus drive groundwater flow down from the unconfined aquifer, where the head is higher, into the confined aquifer, where the head is lower.